Thanks a lot. Now it's good. Right. Okay, so thanks a lot for the nice introduction. Thanks a lot for having me. It's a great, great pleasure for me to be here in South Africa at Stellenbosch and be able to present our work. It's actually the work of a whole community. I'm going to talk about statistical relational learning, also about probabilistic programming, but I'm going to take quite a different perspective than what you've seen before. It's going to be more an AI perspective where you don't just have learning, but also reasoning. And I should stress that this is joint work with some former collaborators, especially Angelika Kimmich, who's now at Cardiff, and Guy van den Broek, who's now at UCLA. So what I'm going to argue and with is something you often see at AI conferences these days, is that you need both learning and reasoning. 30 years ago when I started in the field, I was telling everybody we need to do machine learning. Now when I'm doing learning, I'm telling everybody, well, we should maybe also look back at what the people in reasoning do, and maybe we should actually combine the two things. And there's kind of ample evidence that a number of people that are advocating this kind of endeavor. First of all, from cognitive science, there is the book Thinking Fast and Slow by the Nobel Prize winner Daniel Kahneman, who talks about like two distinct systems. He talks about system one, which is like for thinking fast, and this can do like the kind of things where you don't really need to think about, like 2 + 2, or recognize people, recognize somebody in an audience, recognize as a car where the people are in the street. But then there's also like system two, which is about slow thinking. And that is the kind of reasoning people go to if they solve complex problems. Say if you solve a mathematical exercise, that's the kind of system that you will be using. Also, if you do need to do some complicated planning, that's also the kind of endeavor or the kind of thinking that you will resort to. And that kind of difference comes back in a lot of alternative terms, which do not always mean exactly the same, but are kind of closely related. I mean, some people would call it the data-driven versus the knowledge-driven approach. Others would talk about symbolic versus sub-symbolic. People like Geffner talk about solvers versus learners. And basically, I want to advocate that you need both. And also, SRL is about the attempt in the AI community to really combine the best of both worlds, probabilistic, logic, that's the reasoning side, and then also the kind of learning. And that's also what you see back, I think, in today's deep learning today. If you look at AlphaGo, there is a lot of attention for the deep learning component, but people sometimes forget that there's also the Monte Carlo tree search, which actually a kind of reasoning component. And there's also limitations of deep learning that I think require some kind of reasoning to go beyond that. Like the successes with the Atari games. I mean, they're all amazing, but if you just change the rules of the game a little, then, well, the controllers won't work anymore. For us, for instance, it's kind of very easy if we learn a video game and the task is changed from like survive as long as possible, die as fast as possible. For us, this is very, very easy. That's because we can get the insight, we can capture the knowledge that that's underlying this video games. And today, I think deep learning is not yet there. There's also other people that argue this, Adnan Darwish, Hector Levesque, Josh Tenenbaum, Hector Geffner. If you Google on the web, you'll all see like people and articles and videos claiming for that. Not too much about that. This is just the introduction. To say why we're doing this. We're doing this because we want to get to combine reasoning and learning. And in reasoning, there are like two central paradigms. First of all, there is probability, and I guess there's been a lot of probability last week that you've been exposed to, and I won't focus too much on that, but there's also logic. And I'm going to focus a little bit more on that. So maybe this talk will be a little bit of the outsider story. But still, I'm going to show how you can combine the two and how you can also combine it with learning. And that's actually the question that statistical relational learning, which started about 20 years ago, has been tackling. It's all about combining these three fields in a sense. Of course, there is machine learning, but then there's also like reasoning. in logic, and people have been using databases, they've been using logics, they've been using programming languages for that. That's in a sense the KR community, maybe also the programming language community. Then there is people that deal with uncertainty, graphical models, the UAI community. And then there's, of course, the machine learning community, which is learning parameters and structures of graphical models and of other models. This field, people have been working on for about 20 years, and it's known under different names. It's known under names of statistical relational learning, statistical relational AI, probabilistic programming, probabilistic logic programming, and it depends a little bit at the angle you take, the community you come from, to see which of the elements is most dominant and which terminology people are using. I'm also going to motivate this field by a number of examples of the kind of things we do and the kind of things that thrive us. Here you see like an example of a big database where a lot of information has been integrated. And what you see is like different entities. It's about biological entities like genes and pathways and proteins. And there's also relationships amongst them. Now, some of the information has been crawled from the web, and therefore it's kind of uncertain. And if you focus in on these networks, then it does make sense to kind of make them probabilistic. And here you see, for instance, that there is a receptor, biological process coming from the gene ontology, and also a gene coming from another database that are related to some extent. There is some evidence why they are related. And so that is turned into a degree of belief in a sense. There's many different types of nodes and links in that network. And the nice thing is that you can turn that into probabilistic databases. And these probabilistic databases can be used to return you the most promising answers first. It's also the kind of thing that people do, like if you look at some of the knowledge-based construction work, also like the NEL system, the never-ending language learning system at Carnegie Mellon, is actually also taking an approach which you can perceive as doing this kind of thing. This is in turn what you can use to reason. Here is like some of the applications we did in reasoning about molecular interaction networks, where you give like you turn some observations of biology, and you combine that with such an integrated network, and then you try to find the explanatory graph. You try, in a sense, to find explanations. That's the kind of passes that you have in these networks that will have the most evidence in the light of your data. And biologists are quite fond of this kind of task, because you can also understand the result, what is coming out. It's basically a subgraph of your original network. It's a subgraph that matters the most given your data. Here is the NEL database. It's a snapshot from a couple of years ago, but basically what they do is they crawl facts, and also to each of the facts there is a kind of associated number that tells you how reliable that fact is. And you can interpret that as a kind of probability value, and then you can interpret NEL as a big probabilistic database on which you can ask and answer queries. Other things that are perhaps more fancy, one of the things one of my students, Ingo Toon, did a couple of years ago is look at multiplayer online games. If you look at multiplayer online games, then what you can do is you can represent states of the world in this kind of big networks, where you will have players, you will have alliances, maybe you will have cities. And then, of course, these states of the world, they change dynamically over time. So you typically see a sequence of these states. The question then is, can you build probabilistic models that will allow you to make predictions about what's going on later on? Can you, in a sense, take past data from snapshots of these games? Can you build models for that will allow you to predict what's going to happen in the future? If you're able to do that, then maybe you're also able to play better, because if you can predict what your opponents might be doing, then that will give you insight. Other kind of motivating examples is like tracking, where you can analyze, for instance, video data, and people have been doing that. And the idea is that people sometimes, if you have a reception, people will group and they will ungroup, they will move around, and maybe also there you can try to predict what is going on. The idea is that it's again very much representable as this kind of graph structure. People representing, well, people being the nodes in the graph, and maybe the distance being like the connections. Question is whether you can also build models for this. And then a next example is more in a robotic setting, where you can reason about how to achieve certain goals. And here is, and I'm going to elaborate on that with some real robots in the second part of the talk, which will be tomorrow. I'm going to show some videos there where you can actually learn how to move objects in particular places. And the idea is that in the first step, you will be learning a model. And in the second step, you will be using that model for planning purposes. A last example that serves as a motivation is this one. And that is connected to the Allen AI challenges. It's one of these challenges for the AI community, and it's one that is specifically also about reasoning. One measure of progress in AI is to see the kind of exam questions that we can solve. And so the Allen AI Institute has devoted a lot of projects and a lot of manpower to devising techniques for looking at that. And the idea is there that you typically start with a focused set of exam questions. They're phrased in natural language, and then you need to, provide the right answers. We've been focusing on questions about probability, and this is also like a typical situation where you do need both learning and reasoning. Here you need learning to cope with the natural language, and you need reasoning because there's kind of probabilistic methods behind that. It's the kind of high school mathematics that you need to master, and for which it's the kind of questions, exam questions that you want to get answers for. So all of this requires, all of these applications have a couple of things in common. First of all, like in the multiplayer online and game setting, you've got objects and relationships. I mean, there's like graph structures that represent states and that you want to make some inferences about. And that will argue for the use of relational logic for first order logic, because that can deal with this kind of relationships. The next thing is that there's also typically a lot of background knowledge that you may have about your domain and that you typically want to use. And the last one is that there's typically also some kind of uncertainty. In the robotics case, if you do an action, you're never certain that it will have the desired effect, and you also want to cope with that. And so the challenge there is to combine learning from data, past experience, and to combine that also with reasoning using the knowledge that is available. And that is basically the common theme that underlies statistical relational learning, AI, probabilistic programming, and so on. There is now numerous formalisms that people have been using. And as I said, this started a long time ago. The earliest attempts were already in the early 90s, where people were doing like knowledge-based model construction. And since then, there has been a multitude of different systems that has been around, and you basically see some of them here. And the idea is that all these different formalisms, they have different focuses and different backgrounds. You can characterize them in a couple of big chunks. And first set of them is like really the probabilistic programming languages. You probably heard already this week and also last week about probabilistic programming languages. What you've seen there is like the functional and the imperative languages, where you take traditional programming languages and you inject some probabilistic components in there. There is also a lot of work coming more from the probabilistic database, the logic community, and that's the work that I'm going to focus on. That's also the work that my group has been working on for the last few years. It's also that work that fits with statistical relational AI and learning. And there I was talking about the knowledge-based model construction approach, where you, in a sense, use a logic to construct a graphical model. And again, there have been many different developments. Most famous is Markov logic, but also relational Bayesian networks, probabilistic relational models, and others have been used there. And I'm also going to talk tomorrow a little bit about Markov logic. The difference between the first and the second category is that the first are also programming languages. So given that they are programming languages, they have the power of a universal Turing machine. So they're much more expressive. You can really program in them, which you cannot always do in the second type of system. And so there's different styles of doing that. I'm going to use logic. And just to give you a 3 or 5 minute intro or refresher on logic, here is like the kind of ingredients that I'll be using. The first is like a rule where class, author, and favorite topic are all relations or predicates. And basically what that rule says is it's a relation between books and topics. And you will say that the class of the book is on that topic. That symbol means if, basically. Let's see whether that works. It doesn't. Okay, let's forget about it. So the class is of the book is on the topic if the book is written by the author and the topic is the favorite topic of the author, basically. That's kind of the rule that we will be, thanks. That is the kind of rule that we will be using, and that's called clauses in a sense. As in databases, you can then also write down tuples, like what you have here. They're called facts, and here you say that the favorite topic of Rowling's is fantasy. And then there is like a couple of things you can do with that. You can ask what follows logically from my theory, and that's basically logical entailment. And so here I've got the rule back. I've got two of these facts, namely that fantasy is the favorite topic of Rowling's, and Harry Potter has been written by Rowling's. From these three rules, I mean the two facts and one of the rules, you can basically infer that Harry Potter is about fantasy, basically. That this is entailed. And we will be working a little bit with that. The other view on logic is more a model theoretic one, and then people work with sets of facts. In a sense, these are small relational databases, and they're sometimes called possible walls, they're sometimes called interpretations, sometimes called models. And the question then is, when is such a set of facts, when does it satisfy a particular theory like the one that you have here? Now, what is required for that? In order to be a valid model or to satisfy a set of rules, what you basically want is whenever you substitute, whenever you can make the body, I mean the condition part of the rule true, that you can also have, that you also have in that set that the conclusion part is true. So here, if we map author to here, so book on Rowling's, author on, probably it's kind of the inverse way. Yeah, it's inversed. And favorite topic of Rowling's is you map that one on this one. Then you also know this is the condition part, so you can conclude that also Harry Potter, the class of Harry Potter should be on fantasy. And so the conclusion part also belongs to my model, and that's why it satisfies, in a sense, the theory. And the last perspective is a kind of proof theoretic perspective. If you use logic, then you'll typically build a kind of proofs, and that's also something that we will be using. I won't go a lot on these in details. I don't think the details matter a lot. I don't think the logic you use matters that much. I think it's the underlying principles and ideas that are important for this. And so what I'm going to focus on during a lot of the talk is basically on this probabilistic programming language called ProbLog, and I'm going to relate it to some other formalisms like these functional programming languages. I'm also going to relate it to Markov logic tomorrow. I'm going to relate it to some other things like databases that we will see later on as well. And so the starting point of ProbLog is on the logical side, that we just start with these ProbLog programs. ProbLog is a logic programming language, which is very much in the style that I was talking about. You can specify facts, You can specify rules. This rule says somebody will smoke if he is stressed. This rule says somebody will smoke if he's influenced by somebody else. Why? That is smoking, basically. And you start from this. This is the purely logical view. You could also view it as like a database perspective. This is what people have been doing in databases. And now we're going to change that into a probabilistic database. And the way to do that is to look at the smallest non-trivial kind of possible combination. I think that's always a good idea in science, to look at the smallest non-trivial combinations. And so the smallest element in logic is like one of these atoms. It's one of these propositions. The smallest element, or the most fundamental one in probabilities here, is random variables. And so what you do in order to combine these is like you're gonna make the facts kind of probabilistic. They're gonna be random variables that are independent of one another. And so here you say Anne is stressed with this probability, Anne influences Bob with another probability, and so on. And we're gonna work with that. And then of course we're gonna also do learning. And learning will mean you can either learn the parameters of your models, or maybe you can also learn the rules of such models. There's again a lot of different views in these probabilistic prologues. ProbLog is just one of them, and that's the one that is fitting the distribution semantics. If you look at that in terms of graphs and randomness, then what it basically does is it gives you a kind of random graph model where each of the edges will be in or out with a particular probability. Many of the probabilistic logics are actually part of that framework. And there's other ones that are more based on a kind of random walk principle. And also there you can look at different formalisms, and you get different languages. So I'm going to start with this probabilistic logics with the random graph model, and that leads to the so-called distribution semantics that has been elaborated with different other ways. People have then extended that with programming constructs, with tools to do the kind of decision theoretic reasoning, with not just discrete random variables, but with continuous ones, with time, with semirings. There's today also a lot of interest in combining it with deep learning, and in the talk tomorrow I'll also talk about these combinations of neuro and symbolic methods, where I'm going to talk about our latest results, basically. So the roadmap for today and tomorrow is that I'm first going to look at this at the probabilistic programming part. I'm going to introduce how you can model with these languages, also give you a flavor of what the different choices and the different opportunities are. Then I'm going to focus a lot on inference, because inference is hard. And people in the field have been trying to tackle these complexity barriers by focusing a lot on inference. I'm going to say a little bit about how you can do learning, but for some, learning is just inference. So if you can do inference, then learning becomes typically easy. I'm then going to talk about the dynamics. This is what you need to cope with the robotics. This is what you need to cope with also the multiplayer online games. I'm going to talk about the neurosymbolic part, Markov logic, and then the holy grail of statistical relational learning is the lifted inference, where you don't make just inference at the level of ground theories, because that explodes, but you want to make inference at the kind of abstract level, but more about that tomorrow. So let's start with the modeling, and let me start with our standard example that illustrates how you can model with this. This is like a situation where you have two urns and you have one coin, and the idea is that you toss the coin and you draw a ball from each of the urns. If you will win the game, if the coin comes up heads and there is a red ball, or there are two balls of the same color that have been drawn. And the way to represent that is basically as follows. Here you've got like the coin can come up heads, with probability 40%. It's a biased one. And you can write this down like that. If it comes up tails, then that will mean not heads is true. So this fact will be true with this particular probability. A second example is that if I draw my ball, my first ball, from the first urn, I get a probability of 30% that it's red and 70% that it's blue. And this is what is called an annotated disjunction. It gives you like alternatives possibilities. The last rule is for the third urn, where there is for the second urn, where there are 3 possibilities. It can come up red, green, or blue, each with corresponding probabilities. And these are like the basic random variables that I can represent in this way. And all what I need to do then is add my knowledge to that in the form of logical rules in terms of the kind of clauses that I've mentioned before. And I can say, for instance, you'll win if it comes up heads and one of the balls, I don't care which ones, hence this underscore is red. And here is a second one. You'll win the game if the 2 balls belong to the same color. So that's why, I mean, this represents a kind of variable. And given that the name is the same, you require it to be both red, both green, or both blue in a sense. So to sum, what you have is a number of probabilistic choices, either in the terms of these facts or in terms of these annotated disjunctions. And then you have the rules that capture the consequences. What you can then do is ask the typical questions that you would ask of any probabilistic model. You can look at what's the marginal probability of winning this game. You can look at conditional probabilities. What's the probability that I will win given that the second ball was green? And you can also look at things like the most probable world in which something is true, like MPE inference. But in order to understand the underlying distribution, you should view it as a kind of generative model. And let's go through this generation process by sampling a couple of possible worlds. And from that, you will derive the semantics and the kind of probability distributions that are the correct ones. So in order to start sampling a possible world, you start with the empty one. And we'll then go through the probabilistic choices and sample from each of these probabilistic choices. We'll take one possibilities. So suppose we toss a coin, we sample from that, and it comes up head. That will be with probability 40%. We then go to the second choice. We have to sample from this one. Suppose we sample a red ball, and that's going to be with probability 30%. And we take the third one, where we again sample from the third possible choice. And the second ball is basically green. That is with probability 30%. Then we've sampled from all of the basic atomic choices. And so we do have these basic facts there. All what is left now is to use the rules to complete our possible world. And we do know that in this case, well, given that there is heads and red balls, we do know that also winning will be part of this possible world. And that is, in a sense, completing the sampling process. This is our full world that we are having. You can then look at other ways. I mean, you could first sample, get tails in a sense. You could again get reds. You could again get reds with this probability. And of course, in that case, the second rule would fire, and you would also have to add wins. If you do that systematically, you'll get up with these possible worlds. And every possible world will have an associated probability. These probabilities are indicated here, and that's the kind of underlying probability distribution that you want to use for answering your query. That is the one on which you can, for instance, decide what's the most likely state in which winning is true. You can go through all the worlds, and of course that's not what you will do in practice. It's just to illustrate this. You'll notice that this is the most likely one. You can also look at most likely one where something is false, and yeah, then you'll get this one. I guess that must be true. The more interesting ones are the conditional probabilities and the marginal probabilities. In order to see what's the probability of winning, you will just look at which walls have winning in them, and you'll sum up their probabilities. And then there is the conditional probability that is illustrated here. There you first sort out the walls in which the second ball is green. That's going to be the middle column. And then you look at which of these, so that's the blue ones, and the ones that are winning are the ones of these blue ones that are winning is listed here, and so you get just the division there. And that defines your conditional probability distribution. This is what is called the distribution semantics. It is listed as here. The probability of a marginal query like winning being true is basically the sum over all the possible walls that satisfy the query or that entail the wall, all of the basic facts, I mean the kind of things we generated, and then you take the product of the facts, of the probabilities of the facts that are true, times the product of 1 minus the probability of being true for those facts that are not true in our wall. This is basically the formal definition of what we have done. There is an alternative view, which maybe views it a little bit more as a generative process, which is indicated here, where again you will enumerate these walls in this kind of tree structure. Initially, for this program, your wall is empty. You do know that John's rows with probability 1%, so you go here. Then John's rows, if John's rows, the window will break with probability 60%, so you have these two possible choices. Left is where breaks will be true, so here John's rows and break is true. There just John's rows is true. And then you can kind of descend along these trees until you reach the leaves, and at the leaves you'll get this possible walls being depicted. And again, from that you can look then which are the walls in which breaks are true, and you'll end up, you can just sum up their probabilities. The probability of like this wall is just then the product of all the labels along the way that you have. And it's kind of quite nice in this generative process. It doesn't matter in which order you apply the rules. You'll always end up with the same kind of distribution. And so that's a kind of intuitive way of looking at this. Another way why I'm showing this generative process as a tree is that it's also what is used to look at continuous distributions. And also in continuous distributions, there have been extensions of these logics that work with such continuous distributions. And for instance, if you're in a kind of robotic setting, you want to say, for instance, that if the type of the object is glass, then the lengths will be distributed according to a Gaussian with a mean and standard deviation. And you also want to use this kind of lengths then later on to do some kind of reasoning. Maybe you want to say that you can stack a top object on a bottom object if the length of the bottom object is larger than the length of the top object, and the same holds for the width. And that is the kind of language, probabilistic programming language, that we've been using in a little bit of robotics and manipulation settings. The thing is also very related to databases. If you look at probabilistic databases, then it's very, very similar. It's just that these ProbLog and ProbLog, they're programming languages, and so they have the power of Turing machines, which probabilistic databases, of course, do not have. But a database could, a normal database would represent tables. It would have SQL queries. And you can change these probabilistic databases into ways that will also associate probability values to the tuple in the database, and then you can ask for the same kind of queries. You can then ask, and there is efficient algorithms for doing that, for instance, for the top most likely answers to particular queries. And there's been a lot of work by, for instance, people like Dan Suchu and others on this probabilistic databases. It's in a sense also what is in NEL, although the NEL people are not playing it that formal, but intuitively you see that there is a direct match between the kind of tuples that you have here with, okay, they call it confidences, it's not true probabilities, but you could readily turn that into a probabilistic database. And then of course you can query such probabilistic databases later on. Maybe another example illustrating the power of these logics is actually here. I've said that they, in a sense, are graphical models and they extend graphical models. Here you see a particular plate model that people are probably familiar with. And so what you see is that there is a plate for students. That's the plate here. There is a plate for the difficulty of courses. And then for students and courses, they're also assigned a grade. One way of looking at this is that you can look at all possible students and all possible courses and simply ground out the model. And this is what, graphical models will typically do. But you can also write this down in these probabilistic languages. And maybe we can simply go through this example. The first plate, it's like the intelligence of students. For every student, there will be an intelligence statement. Is he intelligent or not? For every course, there will be the difficulty. Is it difficult or not? You can list your students. You can list your courses. And then you can list also some kind of rules that will allow you to say something about the probability of obtaining which kind of grades. And here you say that you'll get an A if it's an intelligent student and the course is not difficult. There's some more complicated things that you can write down here, like the intelligence. If the student is intelligent and the course is difficult, then, the probability of getting an A is 30%, and the other options is like that. You can do that for a number of other rules, and you end up with something like that. Now, this would be just like plate models, and this is not very interesting. But the interesting thing is that within these logics, you can easily integrate background knowledge, and you can just write this down in the form of rules. You can, for instance, define when something is unsatisfactory. Students will have failed if he fails on at least one of the courses. Maybe you can also get a definition of when students are excellent, and you can build the kind of ontological knowledge, if you possess that, readily in this kind of models. What you can also do is, of course, represent Markov models and Markov chains, like what is done here. Here is just a little representation of a Markov chain. It rains or it's sunny with probability 50%. This is Belgian weather, it's not South African. Then, okay, if at the previous point in time it was sunny, then the next point in time it will be rainy with 40% and sunny with 60%. And you've got the other rule here. And so you can also reason quite nicely over time with these kind of models. And then you can look at limited, you can look at programming. After all, these are programming languages. And here is a little example. If you're going for NURIPS and you're going skiing, which of the objects should you be taking? And there is like rules that you can incorporate there, like every object will have weights. Which ones will you pack? and there will be a probability of this, and the probability you can define to be inversely proportional to the weight, and that is what is listed here. You can also say and program in these logics when there will be excess luggage, and this is what is indicated here in a couple of programming rules, in a couple of logic rules. The details are not terribly important there. So to summarize about this language, what you have is probabilistic choices. That's like the basic. These define your atomic random variables. And then you've got the consequences, which you represent using the rules. What this does is it defines a probability distribution over possible walls. And then the question is, of course, how can we efficiently answer questions with these how can we efficiently answer questions for these programs? Because, of course, you don't want to go through this generative process. Here again, summary of the syntax. You've got the ground facts, the tuples, the probabilistic facts like this one, the annotated disjunctions that if certain conditions hold, something else will hold with probabilities. And then here you've got the more programmed clauses. If people are interested in trying it out, you can look online, just search for ProbLog and probabilistic programming, and you'll end up at this website where there is an interactive tool that where you can specify models and ask to answer queries, basically. There's a lot of variations on these logics. One of the variations is a simpler version, which is called Prism, and the variation is indicated here. What it says basically, if you observe, then the rules here are mutually exclusive. There is no two rules that can fire at the same time, and that will simplify the inference to a very, very large extent. Here the first rule is kind of independent from the others, because the others must be time is always larger than 0 here. So they can never fire at the same time. And then you also see that these two rules will never fire at the same time, because one requires the weather to be sunny, the other requires it to be rainy, and that is the assumption that is made by Prism. If you are certain that your rules are not overlapping, then you can speed up inference a lot, as I will show later. There's another view. I mean, remember that I was talking about probabilistic graphs and random walks. Random graphs and random walks. The semantics that we've seen so far, this is all about random graphs. There's also models that work with random walks. And one of the interesting elements there is the SLPs, the stochastic logic programs, by Stephen Muggleton. And the best way to look at these is to start from probabilistic context-free grammars. In probabilistic context-free grammars, what you get is like just, CFGs. And the difference with traditional grammars is that the rules in the grammar have now been given also probability values. And what you get here is that the sum of the probabilities for rules of one of the non-terminals, like article, you see the parameters for the two rules are 0.6 and 0.4. If you sum that up, that's going to be equal to 1. And that's the kind of property that you do have in these context-free grammars. That's also the property that is used in the stochastic logic programs, and that in a sense allows you to use this to directly assign probability to infer a probability distribution over parse trees. Here you see a parse for a particular sentence, the turtle sleeps, and the probability of this is just the product of all the probabilities of the rules that have fired and that have been used to, in a sense, parse this. And that's the basic for this probabilistic context-free grammars. And then you can lift this. You can put also arguments there, which is what we've done in the logic as well. I mean, it's the difference between first order and propositional logic is that you can use arguments, and in grammar, in grammars, there is the so-called probabilistic definite clause grammars. What they do is they will give arguments to these non-terminals, and they will then require also some kind of unification. Here you see a parse tree for that. There's just one difference here. We now have the article, the singular article A, and then there is two readings for D, two interpretations. It can be plural or singular. And if you then look at parse trees, you get similar parses, but it will turn out that some of the parse trees will no longer be parsable, because if you look at the sentence "a turtle sleeps," that was a legal sentence for the propositional context-free grammar, so the one without the arguments. But now there is no agreement between turtles and A. I mean, turtles is in plural form and A is in singular form, and so this rule requires actually that there is a number agreement between the article and the noun, so this will not be parsable, and that leads to some kind of probability loss. Now, this kind of grammar has been used in the stochastic logic programs. It's also the kind of grammar that has been used and the kind of formalism on which the ProPPR system by William Cohen at Carnegie Mellon is used, is built. And they've used that to develop NEL and a lot of other applications in web mining, knowledge-based model constructions, and others. There's also outside logics. There is, as I said, a lot of different languages around. You probably heard about things like Stan and some imperative languages around here. But most of the languages that started the developments on probabilistic programming in the machine learning community, they're basically functional, like the ones of Church. And Church is actually taking the same kind of perspective with regard to the SRL part. It's just that rather than using logic or logic programs, it uses functional programs on this side, and then also combines that with dealing with uncertainty. So the function that you have here is just a function that will add that will add 5 to a number, and then you will map that onto this list. And so if you apply +5 to this list, you'll get 6, 7, and 8. And what people in probabilistic programming do is they inject random variables. And again, they will look at the simplest, non-trivial kind of way of doing that. And the way of they doing that in Church is what you see here. They've added now this flip construct, and that means that you will flip a coin. It's a biased coin with probability 60%. It will turns up heads. It will return true. With probability 1 minus 60, it will fail. And so if it succeeds, you'll get if true, and you'll take the first branch. You'll add +5. If it fails, you'll just return the original number. And that means that if you map, I mean, if you call this function, you'll get different possible outcomes. And we can have a look at the different outcomes that you will have for this language. I'm not doing it for the full list because, well, the combinations are a little bit too many to put on the slide. But if you apply rand plus to this 1 and 2, you'll basically get 4 possible results, each with a different probability. With probability, 40% times 40%, this will return false twice, and you'll just return x, so x being 1 first, x being 2. You'll just return this one. And there's also the other combinations that you will be getting. You can do the same in ProbLog. Basically write this kind of thing down in a ProbLog fashion, but that's not too important for now. So let's rather look at another case. where you apply the list on 1, 1. So there's two identical numbers in there. What you would guess that church does is every time it encounters this flip, it indeed samples, and depending on the outcome of the sample, it will take one of the two branches. And so the outcomes that you get here is like 1, 1, 1, 1, 6, 6, 1, and so on. If you, on the other hand, look at the ProbLog program, ProbLog will just return two possibilities. It will either say it's 1, 1, or it will either say it's 6, 6. And the reason is that church, whenever it encounters a flip, it basically samples. And so what ProbLog instead does, whenever it encounters a random variable, it samples, but it then memoizes what it has done. So whenever that same random variable is called again later, it will basically reuse that same random variable, and that's why you get only two possible outcomes. Again, you can then simulate that to get rid of this kind of problem. I'm leaving it in the slides. And then, of course, what you can do also is, if you look at church, you can, of course, also implement this kind of gambling game very easily and very straightforwardly in this church language. It's just that, given that ProbLog is memoizing, here you should also do the memoize version of the flip. Church is a functional programming language, and there's many others. Like Anglican is also one of these. The ones that like Venture and many others are all based, in a sense, on this style of reasoning. So it's functional programming where people have injected random primitives. It's also giving you a kind of generative model. It is based on other inference mechanisms, as we will see. And in church, you can do memoization or not. You can actually turn it on or off. And that's also like the difference between these different languages. In church, you have these random primitives like flip. In ProbLog, there are these random facts. Here you do the memoization. In church, you have to define when to do memoization and when not. Here, the underlying programming language is logical. There it is the lambda calculus, it's functional. And one difference is also that the kind of distributions that are specified are quite different in spirit. In ProbLog, you get a distribution over possible worlds, the kind of states and the kind of random graphs that I have been talking about and have been illustrating in this game example. What you get in church is like a distribution over possible traces to your program. And that allows us to, in a sense, summarize this first part about probabilistic programming. What you get is, if you want to build a probabilistic programming language, you start from this programming language, the traditional one, and then you inject random variables. And typically, you're going to inject them where the simplest non-trivial elements are, like the simplest Boolean concepts. Also, you can do similar things for continuous variables. And then you're going to define the semantics. In the starry eye community, people take this possible worlds semantics. It's based on this probabilistic databases. In the functional and the imperative languages, it's rather defining distributions over these possible traces. Yeah, so you get a quite different behavior. The primitives that you also need to add, and that's what I'm going to add next, is the ones for doing inference, how to do that. And then, of course, also how to do learning, where you can do Bayesian inference or things like expectation maximization. The former is popular in the functional language. The latter is popular in the logical language. Okay, so let's look at inference. And the reason that most of the work in statistical relational AI is on inference is that it's computationally hard. And so there's a lot of variations there. And inference is, of course, also the key to learning. There's typically two steps to take. A first view is like the logical one. And in order to start from the logical view, you typically need to reduce it to a kind of probabilistic solver. And the way that people are doing this, and I'll elaborate that, is by either computing proofs or by either computing a model. And using the proofs or a model, you then get a propositional logical theory that you can send to a propositional probabilistic engine and that you can solve. There is also the holy grail of statistical relational AI, where people have been looking at. If you ground out a theory, it will mean that you will replace every variable that occurs there by all the possible constants, and so you will end up with a large database, with a large database of facts, and that is typically leading to explosions. But in lifted inference, what you want to do is you want to retain the variables to the maximal possible extent, and you want to work at a kind of abstracted level so that you don't need to generate this enormous databases, and you can lift in a sense. I'll be talking a bit about that tomorrow. Okay, so let's look at the logical inference first, where you've got the proofs or the models. And let's look at this smokes example with the proofs. Here is one way of looking at the proof for Carl smoking. You see the original program on well, this is just for ProbLog. You have the original program on the right. Carl smokes, and then you can use the first rule. I mean, Carl will smoke if he's stressed, and so you reduce Carl smoking to Carl being stressed, and then you try to see whether that occurs in your database or not. It doesn't, so at this stage your proof fails. But you have another opportunity to try to prove that Carl smokes. That is to use the second rule. And if you use the second rule, then you reduce that to Carl being influenced by somebody, and that somebody is smoking. And you can then go down deeper. You can look at, is there somebody that influences Carl? Yes, there is. Bob influences Carl. And so you can substitute that, and okay, you can reduce what you still needed to prove. You get Bob smokes. And again, you can look at, does Bob smoke? You can try to prove that using the first rule. Well, Bob will smoke if he's stressed, fails, and you continue like that until you find a successful proof. A successful proof will be one which ends up in the empty set of things that you still, the empty goal, the empty set of remaining things to prove. And so this is like one successful branch of the proof. And along the way, the facts that we've been using have been marked in orange and have been written at the bottom. And so this proof relies on the rules, of course, and also on these three different facts. What happens now if we change it to the probabilistic logic? Well, first we do add these probabilities. We do add them here. And you then get still that you can do the same proof. You can also look at how likely is it that I will get this proof. It will be as likely as the product of the probabilities of all these probabilistic facts, this probabilistic things that I've used. So influences Bob Carl was 0.2, influences Anne Bob 0.6, and stressed Anne. So the probability of that proof is as indicated here. And this is an easy case because for that case I could indeed validly conclude there's only one proof. So the probability of Carl smoking is just equal to that probability. But if I slightly change the setting by introducing another tuple, another fact that is probabilistic, I will get two proofs. I mean, I still get the original proof that is listed here, but I now get another proof that is indicated here. And now it is very tempting to say that the probability of the original goal that I had, Carl Smokes, is just the sum of these, the probability of these two proofs. But that doesn't hold in general. Anybody seeing why that doesn't hold? Basically, the proofs are not disjoint, and of course, they can overlap. And so what you get is the kind of disjoint sum problem that leads to all the complexity problems with this kind of computation. You can also see it here. I mean, here are like, we list the possible walls all explicitly. And you look at the first proof. Well, that matches 2 out of these. If you look at the second proof, that matches the last 4. Now what you see is that the intersection is not empty, and so if you would just add up the probabilities of the 2 proofs, you would have counted the intersection twice, and that is of course not a legal thing to do. You would have to change that. That is the thing that leads to the all the problems. You can then look at what people have done in databases, and there is indeed some pretty nice results in the database community. The pretty nice results are that if the queries that you post to your database have a fixed size, and the size of the query is much smaller than that of the databases, then the complexity of evaluating queries in the size of the database, the data complexity as it is called, is all polynomial for standard queries, so the ones that don't involve recursion in that. Now what you can solve, what you can show for these probabilistic databases is that you really, things are not that easy. You can show, and I'm just going to show the result. Again, leave some of the explanations on the slides. What you can show is that for the kind of queries that we're looking at, so a union of conjunctive queries, so Carl Smokes and Bob Smokes is like one conjunction, and then a union thereof is like just a disjunction of such conjunctions. You can show that the evaluation of such queries will be either polynomial in the database, or else it will be sharply hard, and that means it's a counting problem that belongs to this kind of complexity class, which is way harder. Here is 2 examples. This query can be solved in polynomial time. This one is no longer in polynomial time. This one is so-called sharply hard. And that's why people resort to a lot of approximations, a lot of techniques also, a lot of compilation techniques, and that's what I'm gonna talk a little bit about now. One technique that is very fashionable in the graphical model community and the statistical relational AI one is what is called knowledge compilation. What you do in knowledge compilation is you take a logical formula and you compile it into a particular type of circuit. And typically the compilation step is quite expensive. I mean, that's where you push in the computational, where you put in all the computation. And then afterwards, when you get the circuits, the evaluation becomes easy. And so on the, let's revisit our example with the smokers, with disjoint sums. And let's look at how these decision diagrams, these knowledge compilations would work. In knowledge compilation, there is different classes of diagrams. The most simple and also the earliest one is by Bryant in '86, and at some point, not too long ago, this was the most cited paper in computer science, according to cites here. And the reason is that really a lot of different techniques are exploiting that, techniques in verification, in computer architecture, in graphical models, and so on. And so what these BDDs offer is a very compact graphical representation of Boolean formulas. Let's look at a simple example. Let's look at this formula, and we can look at what it does. I mean, here are all the possible assignments of ones and zeros, of trues and false to these three variables. We can then look at which ones are true, which ones satisfy the formula. All will satisfy the formula except the first assignment. And what we can build is a kind of decision diagram. This is like a type of decision tree with some differences. First of all, you see at every layer there is always the same variable that is appearing. So first layer is x, second is y, third one is z. Secondly, the left branch, I think, is always the false branch. The right one is always the true branch. And what this is like the most explicit and the most expensive representation, but you can simplify it by doing merge operations. The first merge you can do is like, well, let's merge all the ones into one node. And so we get a DAG instead of a tree. And then what you see is that the x from z, both the true and the false branch, they're all pointing to 1. And so these occurrences are basically not necessary. We can basically skip testing on the value of z, because whatever the outcome, true or false, is, we will still go to the 1 branch. And so we can delete the z branches. If we do that, we get this one. Here we've got the y branch. And again, for both branches, they point to the 1. And so we can again simplify that. And that would be one of the resulting BDDs for this kind of theory. And the interesting thing is that from this kind of theory, you can now represent, you now have an equivalent representation to the original formula, but the representation is such that you can rapidly compute your probability values, and that it's kind of disjoint. So the first one is giving you the x. The second one is giving not x and y. That is listed here. And the third one is not x, not y, and z. And that is the one that we get there. Now, all of these three components now are mutually exclusive. And that means that if I need to compute the probability of this formula, I can now say it's the probability of the first plus the probability of the second plus the probability of the third. And I've solved, in a sense, this knowledge compilation problem by compiling to a BDD. Here is another, here is the BDD for our little toy problem with the two proofs. You had the longer proof and the shorter proof. And what it does, if you compile it to a BDD, is you'll see that this edge is inserted. And that means that you will add a particular node here, which is not stressed Bob. And by adding not stressed Bob here, you again have two disjoint formulas, and you can kind of add the probabilities. So this is we can now compute the probabilities in a kind of bottom-up fashion. Left, you will have a probability of 0, because that's, of course, the 0 node. 1, you will start 1, and then you will go bottom-up in a sense. This denotes stressed Anne. She was stressed with probability 80%. And so what we'll get to compute the probability of that node is, well, we'll take 0.2 times probability of this one, 0.8 times that one. And so that will give us the probability of this node. And so you can kind of propagate these probabilities upwards to end up with the desired probability of Bob influencing Carl, in a sense, in our domain. So the idea with knowledge compilation is that you're going to query once, and you're going to query many times, but you compile only once. So you start from your Boolean formula. that you found using proof techniques or model theoretic techniques, and that you then will query many times. Also, Bayesian networks can easily be represented in this kind of framework and would also be compiled to such circuits. Should stress there's different and better, much more compact representations than these BDDs that people are using. There is the SDDs, there is the DDNFs, and so on. It's also the state of the art in Bayesian network inference. And so this is what we do, or what we did in our initial approach to ProbLog inference, is we would compute all the proofs and then compile it. We would compile this into the BDDs and then take it from there to compute the probabilities. There's also a more model theoretic approach, where rather than computing all the proofs, you look in a sense for a different way of doing that, and you're going to generate models. I've already indicated how you can turn databases like this into models. This is just a normal logical database. You would do the kind of forward reasoning from these facts. I mean, you start from these facts and you would add all possible conclusions until you cannot enter any further facts there, basically. This is what you would do, and you would end up with a model. In order to answer the query then, whether Carl smokes or not, you would just see, does it occur in my model, yes or no? Here Carl smokes is in my model, and so you would conclude that. That's also one of the ways that you can do that. It's this way that is used in what is called weighted model counting, and that's another framework that is frequently used in the star AI community. It is frequently used to in probabilistic computation. And the way that this works is that in the first step, you will take the probabilistic theory, the theory that is listed here, and you will ground it out in order to get something like that. You will cleverly ground it out so that the formulas that you will get don't explode too much. You will try to take into account the query so that you only look at the relevant part of your theory, and then you'll convert it into this propositional logical formulas. For instance, here you see there's two rules for Bob smoking. And what you will do is you will combine these two rules in a kind of unique statement like that, which is in propositional logic. And so what at the end of the day you get is a conjunctive normal form that you can reason with. And that will be the basis for this weighted model counting. Now, weighted model counting is, you can do that with knowledge compilation, but you can also do it with search techniques. And here is another kind of interesting connection and generalization to what people do with inference in Bayesian networks. If you do inference in Bayesian networks, then, well, you want to, for instance, in this network, compute the joint probability of E and particular value for G. Then what they do is, you know, the traditional marginalization of all the variables that you're not interested in. Then you replace it by the joint, and then you've got these huge summations there. And so what you get at the end of the day is a sum product version. Now, sum product is also the basis for SAT, number SAT, and weighted model counting. There is some kind of interesting analogies to be made between these logical versions and these probabilistic ones. If you want to look at the original SAT problem, here the task is to find a satisfying assignment of this A or B or not B of C, and not B or C. And you can view this as like taking a kind of disjunction over all possible assignments that I can make to my variables A, B, and C. That's like what I will get here. I can actually substitute A and B and C by true and false. And so what I get is like a huge disjunction after assigning true and false to these variables. If you then look at this one, A or B, that's in a sense a clause, and I'm going to just write it down as a factor as you would do it in the graphical models. It's just the clause having these two variables. This is just the other clause having another variable. And then you can take it from there. The set formula can be viewed as like a disjunction over conjunctions of these factors in a sense. And each factor corresponds to one of our clauses. Now, the interesting thing is that, okay, this is disjunction and conjunction, and we're looking at set. Does there exist a model? Does there exist a satisfying assignment of truth values to these variables or not? In number set, you're not interested in looking at a satisfying assignment. You're interested in finding out how many satisfying assignments there are, basically. And that's like the intermediate step to go to weighted model counting, where each of these satisfying assignments will get a weight, and that's what we will be using for the probabilistic reasoning. And so in order to change the previous version into number set, all what you have to do is change, in a sense, the semi-ring. Here we're working with the Boolean operations. There is a Boolean sum or disjunction, and there is a Boolean conjunction. What we now do is we just work with the natural numbers. And we're gonna assign this the value true. If this is true, it's gonna get the value 1. And we're just gonna now sum over the over all the assignments that actually satisfy that, and we're going to take the real sum, not just the disjunction. And so what you get is something in this form, and that gives you the number of satisfying assignments. And you can then change that to weighted model counting. What you do in weighted model counting is that every assignment will still get a weight, and the weight will be simply the product of the values corresponding to the variables. So remember, when we were talking about these probabilistic facts, they had a probability P. And so the weight of that fact would be P in case A is true. It would be 1 minus P in case it is false. And so again, you can represent that as a small change with regard to the original set and number set problem. So the weighted model counting problem in general is typically found in papers in this way. Here you look for all satisfying assignments of your formula. This is the formula that you feed in. This is the list of all satisfying assignments. And for each satisfying assignment to your logical theory, you will compute this weight by taking the product of all the literals in that satisfying assignment. This is what is listed here. And so in the case of working with probabilistic models, you'll get P for the positive one minus if the negation of the literal is in there. On a little example, if you look at A or B and not A or not B, you can look at what are the two satisfying assignments. Well, this will be true in two cases. This formula, it will be true in the case that A is true and not B is true. And so you'll take the product of the weights for that possible world. And will also be true in the case that B is true. It's the other way around, right? So this should be not A is true and B should be true. So this should be not A, basically, I think. And then there is still extensions. This is the discrete case. There is an extension called weighted model integration by Bell et al. At UAI. Was a best paper award that is basically showing how you can extend this weighted model counting to do weighted model integration to also cope with continuous distributions. And this is what is used then in ProbLog. What you use in ProbLog is basically in the current version of ProbLog, you ground it out cleverly, you assign the literals the right kind of weights, and then you call a weighted model integration, weighted model counter to give you the correct kind of answers. I don't know whether I still have a lot of time. 5 minutes? Okay, in 5 minutes I can still give you a flavor of how the underlying algorithms work. If you're familiar with DPLL, then that's the one that you typically see in standard courses to do logical satisfiability and find a satisfying assignment. Now, the DPLL can be easily extended towards solving weighted model counting problems. And it's this which is the underlying algorithm, in a sense, also for a lot of the for a lot of the weighted model counters, for weighted model integration, and also some of the knowledge compilation techniques are also built on that. So what you do is, in all of these, you have like a sum over different variables, and then a product over different factors in terms of these variables. All of the problems, SAT, number set, weighted model integration, and weighted model counting and weighted model integration can all be written in this form. And there are some properties that hold about this plus and multiplication. They're called semirings. Plus and multiply typically are commutative, associative. Typically also the product distributes over the sum. And then you've got a zero identity element for the addition. And you've got annihilating elements for both. And then you've got also an identity element for multiplication. And that's kind of in line with what semirings are having to offer. And so it's because of this property, because of the fact that you work with semirings, that essentially the same algorithms are applying. Here is the kind of algorithm that underlies all of these. What you end up with is you start with all the variables. Remember, my variables, I've got variables. X will be part of these variables, and of course all of these. And I've got also the factors there, right? And the factors you can write as sets, like what do they have in a sense. And so you start with variables and factors, and then the first thing is, okay, if I don't have any factors left, I'm gonna return a 1. Otherwise, if I can evaluate one of the factors directly, I'm gonna do that, and I'm gonna call the procedure recursively, and I'm gonna multiply by the result of that factor, and I'm gonna call it recursively without that factor. In the other case, I'm gonna select, in the other case, there's no easy solution. I can't really simplify the formula directly. So what I do is I take one of the variables and I set it to true, or I set it to false. And so I get two subproblems, and I do a recursive call. In the first recursive call will be with without this variable that I just assigned, and it will have every occurrence of that variable in the formulas, in the factors, replaced by true. Secondly, for false, basically. And so that's the algorithm that you get there. You can simplify it a little if you go and look for the purely logical version. If the empty set is a factor, the empty set is a disjunction. So if there is nothing in the disjunction, then you're always gonna it's always gonna be inconsistent, and you always need to return false. And so this is the basic, a little bit simplified version of DPLL. You can illustrate it here. This is our formula. We wanna get X or W and Y or Z. That are our two factors. The variables that we have are X, W, Y, and Z. And then in the first case, well, we don't have that the empty factor or the empty set or the empty disjunction is in there. And we also don't have that the set of factors is empty. So we can't simplify. So we have to choose a variable instantiated. We do that, we substitute it by 0 on the left, by 1 on the right, and then we simplify basically. If W is 0, then X or 0, X or false is just X. And so the simplification of this is indicated here. If W is 1, then X or true or X or 1 is true. So that factor can be left out, and you get this as the resulting formula. You can then do that recursively. In this case, you take X equal to 0. If you take X equal to 0, what you notice is that X gets the value false, so remove it, and you get the empty set. Now, the empty disjunction is not satisfiable, and so at this stage, you won't get any solution. You'll just have to return a 1, as also predicted by our algorithm, or prescribed by our algorithm. And you can recursively go down in very much the same fashion in the other branches. What you see is that there are succeeding branches where you get a 1 here, here, and that will give you satisfying assignment. So the choices you made is W equals to 0, X equals to 1, Y equals to 1. That gives me a satisfying assignment, and so I found a solution. Now the interesting thing, and that's why I'm showing this, I just need like 2 more minutes, so the interesting thing is that this can easily be extended towards counting how many models there are. The only thing that you need to do is, again, like change this Boolean semiring to the natural numbers and change your algorithm a tiny little bit. I mean, the algorithm essentially remains the same. It's just that here we're not going to say that 1 plus 1 is 1, as it is in Boolean logic, but 1 plus 1 is now 2. As it is for the natural numbers. And the other thing is that here, if our set of formulas still to satisfies becomes empty, then we do know that there is a solution. And we just count how many solutions there are, and that's going to be 2 to the power of the variables, that the number of variables that are still remaining. Looking at our number set problem, that means that you get this style of techniques. I mean, the succeeding branches that we had before, they're still succeeding, but at the lowest level, that is actually level 4, there will be an assignment to all of the 4 variables, and so we'll get a model that counts for 1. Here, I've just specified W, I've specified X and Y, but I've left the choice of Z open. And so given that the choice of Z is open, that means I can take true or false, and I get 2. One level higher, I get 2 to the power 2, that's 4. And so basically this gives me the number of satisfying assignments. Next step is that we do this for weighted model counting. And in weighted model counting, there's 2 changes that you need to make. I said if you do weighted model counting, every assignment will have a weight. That weight will be the product of the literals that are true in there. And so we'll have to take that into account. And so before calling the result that is returned is basically taking into account this literals and this weights of the literals here for the positive one on the positive branch, there for the negative ones. And so also there it is pretty easy to change that. And here, instead of having 2 to the power the number of variables, it can be, if you're not in a probabilistic setting, if you're in the pure weighted model counting setting, where your weight could also be any kind of number, then you just still have to add the 2 numbers for each variable, the positive and the negative, and then still take the product. But that's the only changes that you need to make. And then there is like improvements upon that. People notice that certain branches are the same, and so you can do some caching and so much more fancy things on the basis of that. Okay, so that's gives you a flavor of what people in probabilistic logics are using for inference. It's typically a reduction to propositional formulas. These propositional formulas are then either sent to weighted model counters or to a knowledge compilation procedure that will actually solve the nasty inference problem. Tomorrow, what I will be talking about is not a lot of inference anymore, but I'll talk about learning, how you can use these probabilistic programming languages for learning. I will also talk about how you can mix them, and that's kind of an emerging, pretty young trend in machine learning, how you can merge the neuro with the logic style reasoning, so neurosymbolic. And I'll also talk about advanced inference like this lifted, and a little bit about dynamics. So dynamics, the kind of applications we have been doing with the games and with the robotics in a sense. So thanks.